Okay, so let's continue with what we started last time. And let's see if there is a way to switch the lights on. So what we started last time was the construction of confidence intervals and hypothesis testing for a single coefficient in regression. So if you remember, we had a linear model, and then we had our E2 assumption, the Gaussian assumption and the noise, and this led to this distribution for beta j, transpose X inverse j. And so from this, we constructed a pivot, which was basically, again, to remind you, beta hat j minus beta j divided by the standard deviation of beta hat j, which would be this quantity, sigma square root X transpose X inverse jj. So that's the standard deviation. This would be normal. It means 0 and variance 1. This is a pivot in terms of actually both beta j and sigma, but if you want to pivot only in terms of beta, we replace the unknown sigma with the estimate. So this would give me standard error, which is S root X transpose X inverse jj. And so this would be t n minus t minus 1. Okay, and so this is the proper pivot for beta j. It's like a quantity that depends on the unknown parameter beta j and the observations, whose distribution does not depend on any unknown parameters. Okay, and then we can use this to construct our interval. Basically, I'm going to look at this event that the probability that size of t is less than or equal to gamma. I choose gamma to set it equal to 1 minus alpha. This can be done because the distribution of t is, sorry, the capital T is a t distribution. And so this gamma turns out to be this quantity, this particular quantile of the t distribution, as we argued last time. And so when you rearrange this event, it would just be equivalent to saying that basically beta j belongs to this kind of interval. Okay, so you get from that pivot, if you do rearrangement, we did this last time, you get that basically beta j belongs to that event is equivalent to the absolute value of t less than or equal to gamma. So because that event holds with probably 1 minus alpha, this would be a 1 minus alpha like quantile, or like 95% quantile if alpha is 0.05. Okay. So last time we did not get to do the matching hypothesis test like p-value picture, but I'm going to do it either quickly to finish now and then extend this today with inference for the regression function and potentially new observation, which leads to the prediction interval. And if you're lucky, I'm going to talk about something kind of modern, the modern way of doing it under minimal assumptions. So this stuff is basically developed like 100 years ago. The thing that I wanted to talk about is like the things that are developed in like past 5 to 10 or 15 years. It's a very exciting area, has been exciting area in statistics. So I'm trying to see. Okay. Um, Now, so let's do the hypothesis testing rather quickly. So let's say I want to test whether beta j is equal to beta star j, which is a known value. For example, this could be 0. And then versus whether beta j is not equal to beta star j. And so if I evaluate that pivot, so this pivot works under the true model. So if the true model, let's say under null, we know that beta j is beta star, so I can plug in beta star j there. So evaluate the pivot at the true value under null. Then under null, this is the important thing. Under null, t will have the t distribution. Under alternative, it wouldn't because the true beta would be something else. So whatever that something else is, if I plug in here, that would have like a t distribution, but I don't know it. So this distribution will only hold under null. Okay. Um, or in other words, before we had like this general picture that at the pivot like is a function of both y and theta here being beta j, and now we evaluating it at basically theta equal beta star j, which gives me this a statistic which is only it's really a statistic because it only depends on the observation of beta star j is a known variable. So you can use this as a test statistic if you know the distribution, and we know the distribution. What happens is I can now compute, for example, a p-value, which is equivalent way of constructing the test that we discussed. So here I'm going to distinguish between the observed value of quantities versus that abstract random variable. Okay, so t is a very random variable. So it represents an ensemble of values under null. I'm going to see one realization practice often. So let's say that's t observed. It's a fixed number. And then p-value would also be like a random variable, which is transformation of t. But I'm going to observe a single value of it, let's say, which can be just written as this. If I want to project based on the large values of t, which is what we want to do. So last time I did kind of gave this function a name. So gu is probability under null that t is bigger than u. And so if you evaluate it again at the actual observed value, so if you evaluate at the random variable, this would be a random variable. It would have a uniform distribution. If we evaluate it at the observed kind of, I'm going to be, let's say, a little bit pedantic here. If I evaluate that the observed value would be a number, and that would be the realized value of the p-value. Some people would call that p hat p-variable, if you're really pedantic. This is a p-value that's p-variable, but I mean, often that's just called p-value, but you have to maybe make sure you understand. So this is going to be a number, and this really is going to be the probability that t distribution is more extreme than what we observe. So we are basically evaluating the probability or the mass in these two tails. Okay, the observation under null, the random variable being above this absolute value, observed value, and negative absolute value. And so if I, so far so good. Okay. So that's how we calculate the p-value, and then the decision is the rule is like reject when p hat observation is less than alpha, less than or equal to alpha, which would be kind of equivalent to, because this is like this. If you rearrange it, you can see it's just equivalent exactly to the absolute value of the observation being bigger than that threshold that we have seen come up so many times. The same threshold as in the CI. So either way is going to work. So you can either say if the absolute value of the observation is bigger than that quantile of t, we're going to reject, or you calculate the p-value, you say p-value is less than alpha. This is kind of, you can see at this point, there's no information anymore that you need to retain, it's just alpha. There you need to like just the fact that it's a t distribution comes in. But by the time you calculate this, you already use that information. Anyway, so this is what we get. And it's also equivalent to testing whether beta star j does not belong to that interval. So you can also argue for yourself that this is really equivalent to, by the duality, either one of these would give you the same answer. You either compare the observed p-value to the alpha. If it's less than alpha, you reject, or you look at the observed value to the statistic. If it's bigger than the absolute value, then that particular quantile, you reject, or you look at the confidence interval that you built. And you can easily see from the definition that these two are equivalent. You know, if beta j is not beta star j, that's the value, let's say, could be 0, is not in that interval, then you reject. Okay. That's kind of the same idea. Any questions? Okay, I'm assuming that these are kind of familiar. So there's an example in the book for a simple linear regression problem. On the slides, it's like abbreviated as SLR. It's like a hardness example. I can look at maybe chapter 2, or maybe it appears later as well. There's a prediction problem about two properties of a spring, I guess, like hardness and tensile strength or something like that, how much it compresses or so. I forgot. But you have 14 observations. One variable, you try to predict the other. So it's really the simple linear regression. You have just a single covariate. And we want to test whether, let's say, beta 1 is 0 or not, whether this variable has any effect on the other variable. And you do calculate, like you just do the least squares, I mean, I'm not showing the data, but you just calculate these two. These are really, if you want to be precise, these are the observed value. Okay, usually you don't write the observed, but I just want to make sure that you understand. So this standard error is a random quantity. Okay, it represents an ensemble. So this itself has like a distribution. Beta hat 1 is also has a distribution, but the observed values are what we actually observe in a single realization, and these are the values. And then the 95% confidence interval would be, this is 1 minus alpha over 2 if alpha is 0.05. The degrees of freedom is like 14 minus 1 minus 1, and turns out to be 2.14. And then you get, this is the confidence interval, the observed one, let's say. Value plus minus gamma times this is the standard error, right? And so you evaluate it, you get this interval. Okay. And if I want to do the test, let's say test whether beta 0 is 0. Again, the test statistic is in general beta j minus, let's say, beta star j divided by standard error of beta hat j. This is beta hat. And so this is 0. So I just get the realized value of beta hat j divided by realized value of the standard error. And so that would be t observation, just negative 37. And so the problem, like the observed t value would be how likely that the t distribution, 12 degrees of freedom in absolute value, is bigger than the absolute value of this number. And that's very unlikely. So t is like as the degrees of freedom grows, it just approaches the normal by kind of the law of, by the CLT actually. And so, you know that the normal variable is very unlikely to take it. Like a standard normal is like with 95% chance is between -2 and 2, say. Very unlikely to you draw a normal value of C37. This is a T, so it's heavier tail, it's more likely, but as the degrees goes up, it becomes less likely. And it turns out in this case, it's like 10 to the -14 times 86. So this is less than, certainly less than 0.05, the nominal or the standard significance level alpha, so you would reject the null, right? Overwhelming evidence against the null. Um, so does it mean that the null is not true? Does it mean the alternative is true? What does it mean?
Under alpha, we get
At the level alpha, we reject the null, yes. But what does it mean? What can we say about the null? See if you kind of followed what I discussed last time. Yes.
so I'll try this. So then by frequentist approach, then if we were to take this value, 95%, the time would not be in the confidence intervals we would make from this value would not be
So 95% of the time, if you repeat the experiment, everything would change if you repeat the experiment. All these numbers would change. And so the p-value would change, beta hat would change, and standard error would change. And you may, or this may or may not hold, but if you keep the rule, you reject whenever you're less than or equal to 0.05, you could be sure that 95% of the time, out of however many, let's say if you do it 100 times, about 95% of the time, if you're under null, you incorrectly reject, just like 5% of the time. Okay. This particular, in this case, it has no meaning. It doesn't tell you anything, to be honest. Okay. You can be like, reassure yourself that maybe the null is like, you can like convince other people, but if you have taken a statistic, this has no meaning. The statistics is about like the aggregate, at least the frequentist approach. So really, just as itself, it's not. If many people do the experiment and they stick to the rule and you aggregate, then maybe. I mean, take it with a grain of salt, but if you understand the frequency perspective, this particular one, this particular realization, it could be one of those cases where it's odd. It could be one of those cases where it's kind of like contains the truth. In itself, it's not. So you can just say it's very unlikely that this happened under null, but it's still likely. It could happen, but just one flip of a coin, which is very unlikely, would be or still you could be unlucky. But it's just like a, however you want to interpret it. It's just one realization. There's nothing certain to say. Anyways, I'm gonna keep leave it at that, just for your own sake to make sure. And the duality check you can check. This is equivalent to, so if you're rejecting, then because the confidence interval is built from the same pivot, rejecting this rule is going to be equivalent to this rule, whether zero. I mean, we reject if zero is not in that interval, and that's exactly the case in this case. Okay, so this part you can be sure. If this is true, then this is true, or vice versa. Okay, but whether that if they say anything about the null, it's like the leap of faith that you're taking, just based on a single realization. Sounds good. Okay, don't say that it doesn't have any meaning if you go outside this room, but just know that it doesn't have any meaning. Okay. Uh, so, how we can extend it? We can extend uh, the linear functionals of beta. So this whole thing just extends very easily to, let's say if I define a new parameter, I get a theta, which is A transpose beta, and this A would be A0, A1 up to AP. It's transpose beta 0, beta 1 up to beta P. And then you would get AI, beta I from 0 to P. So it's linear combination of betas, and then let's say A's are known. Okay, so I have a given A, and this defines a new parameter. Okay, so for example, if I pick A to be just, let's say, 0, 0, 1, 0, 0, 0. If I do this, A transpose beta, it would select one of the elements. Let's say the first one is beta 0, the second is beta 1, this would be beta 2. Okay, so individual betas can be recovered as a special case of this by the choice of this is, let's say, E2, the second basis vector. So if you take A to be a basis vector, then you can recover individual betas as the parameter, but it could do more. So for example, if one of the entries is 1, another one is -1, and the rest is 0, you get the difference of two betas. Okay, so you can test, for example, whether the difference of two betas is 0, which is equivalent to testing whether they're equal. Okay, so you could do these type of tests easily if you test for this parameter, for example, being 0. Okay, the parameter is clear. It's a new parameter I define, and I can estimate it. What is the natural estimate of this quantity, theta? So the only unknown is beta, and we have an estimate of beta. I can plug in beta hat. So I get the plug-in estimate. So theta hat would be A transpose beta hat. It's a perfectly fine estimate, right? Um, so-called plug-in estimate. So how do we build like other machinery, like the pivot and do the confidence interval? How do we do it? What is the first step? Yes.
Get the distribution of.
Great. Yes. So the first step would be to figure out the distribution, which is, let's say, under E2. The first step would be to say what the distribution of this is and what is the distribution.
So it would be A transpose beta hat,
Right.
and then variance of
Covariance.
S. So it'll be S squared, and then
So covariance of theta hat, let's say, which is the covariance of A transpose beta hat.
yeah, so you have
No, go ahead.
so you have A transpose covariance beta hat A.
Yes. And covariance of beta hat is,
S squared S transpose X.
it's not S squared, it's sigma squared. Right. That's the true covariance. Okay, so then like sigma squared comes out. So I get a sigma squared A transpose, this should be transpose, X transpose X inverse A. So what is the actual distribution?
Normal.
Normal. So why is it normal?
It's a linear combination.
Linear, yes. So it's a linear combination of the elements of a linear transform of a. So beta hat is already normal, we saw. And so this is just a linear transformation. Okay, and so again, like this is theta. And so in particular, you see that theta hat has the mean, the parameter of interest. So theta hat is unbiased for estimating theta. And really, the only thing that changed here is compared to the beta is like this, the form of the, rather than the diagonals, we're now forming like a linear, the general quadratic functional of that matrix. The rest is kind of essentially similar. So the next step would be you just repeat the process that exactly we did. You can, for example, construct a standard normal out of it by this would be the standard deviation of theta hat. If I divide by this, so this is actually squared. So if I take the square root of it, it would be a standard deviation. So I can standardize and it would be normal. 0, 1. And if I divide this instead by the standard error, which is the estimate, so that one would be T. So this is really that S comes in here. So it would be S root A transpose X inverse A. Okay. So this is now a completely perfect pivot in terms of like only involving theta. Okay, now I can just do everything that I did before. So this is now going to be my T, right? And then you can, I mean, the rest is really, it's not worth writing because it's like exactly the same. So that has a T distribution, so I'm going to figure out the gamma that satisfies this, and that gamma ends up being exactly the same kind of quantile, 1 minus alpha over 2, and then you do the little bit of algebra, so um, you get that the probability that theta belongs to theta hat plus minus gamma, standard error of gamma hat, sorry, theta hat is just 1 minus alpha. Okay, so that would be our confidence interval. So nothing really significant changes here except that our estimate is now plug-in estimate of that quantity, and the standard error is just like that, then this quantity. Okay, the form of the interval is similar. The gamma is exactly the same. The whole thing, this entire sort of reason is like this t is just exactly, you can write it as d divided by that u times n minus p minus 1, where z and u are independent. And the degrees of freedom is coming from basically the degrees of freedom of the residual. It comes from that s that appears in the denominator. So I encourage you to do it again for yourself. If you go through the argument, you just really see it's exactly basically the same. So z is defined as theta hat minus theta divided by the standard deviation of theta hat, and u is that kind of n minus p minus 1 times s squared divided by sigma squared. So that would have a chi-square distribution with that degrees of freedom because it's just the norm of e squared. And so when you divide, you get p. And z and u are independent. It's just exactly the same argument. Okay, and so that's the details. So confidence interval is that. Gamma is the same. The special case is where A is EJ, which is the canonical basis. So you get the beta J. So that's the previous thing that we did. We could have just done this equally. Like it's equally easy to, we could have started with this and just get the beta J for free. The other is we can just set A to be a generic X. And that's just a renaming. And that would give me um, the so-called regression function. So you get X star transpose beta. So what is this X star? It's just a notation so let me remind you what the setup is. So we have like the Zine matrix is containing, we usually view it column-wise in terms of variables, but it's really row-wise, it's just individual observations. So you get y, xi1 up to xi So these are all the variables for a single sample. And so I could potentially write it as x tilde I transpose, let's say, the ith row. And when you multiply by x beta, if you look at the ith row, it's just exactly going to be xi tilde transpose times beta. So when you multiply the x beta, the ith row would be the ith row times beta. And so really, this is going to give me yi is xi tilde transpose beta plus epsilon I. This is the functional form of the relation between y and x. Okay, so this week I can write it as mu of xi tilde, where really mu of x is x transpose beta. This is just a linear combination of the coordinates of x. And oftentimes I write like in this here, I'm going to write it like this to avoid confusion with anything else. This is really, let's say, a generic point. Okay, so you can think of it a generic sample comes in, with the generic set of values for these variables. So let's say x star 1 up to x star p. Okay, so this is really the functional form. If it was a simple linear regression, this just would be a linear function. Okay, it would be, to be honest, it would be an affine function. It would be like beta 0 plus beta 1 times x star 1. And if you plot it, so simple linear regression, it would be like mu of x star is really going to be beta 0 plus beta 1 x star 1 if you want. And if you plot it, this would be x star 1, this would be mu of x star, this would just be a line. Right, so that's regression line, and in general, we need a regression function. Okay, it's a multivariate function. It's like a linear function in Rp, or really in Rp plus 1. And so you can see that if I just rename this A to be this x star transpose beta is really mu of x star. So really this A transpose beta, you can interpret it as, once you rename it, as evaluating the regression function at a particular covariance. Okay, like a vector of covariance. And so in particular, just rename every A in the previous slides to x star and rename. So this was our theta. Now it's like, sorry, this was theta. Now this is going to be theta hat. Theta hat would be an estimate of, so this would be an estimate of the regression function at that point. Yes.
So canonical basis is just a vector of ones.
Okay, canonical base, this is like a vector that has a single one in the j coordinate, the rest is zero. Right, right. So for example, in R3, E1 would be, okay, I actually do the 0. So it's like E0 would be, we start from 0. So it would be 1, 0, 0. And then E1 would be 0, 1, 0. And then E2 would be, I mean, if you have the intercept, I would say, let's index the coordinates by a 0-based index. And yeah, these are the ones. Okay. So if you do that renaming, basically we're estimating the regression function at a particular point. That will be my estimate. It will be normal with this mean. That's like theta. That's theta hat. And this is like A transpose, X transpose, X inverse A. That's just now, in terms of A, you have X star. Okay, so you have the distribution, then you repeat. I mean, you don't even need to repeat. Okay, everything just follows by renaming. Standard error is that. The pivot is that. And then you get the confidence interval for mu of X star, which is mu hat X plus minus En minus P minus 1 times 1 minus alpha over 2 times the standard error. This again, this is gamma. This is really nothing but the previous slide, just renamed to interpret things as the regression line. Okay. Does this make sense to people? Just remember the mu of X is really just X star trans. This is known, like you're fixing a point, and mu hat of X star is just its let's say estimate, which is the same X transpose times beta hat. Okay. And then you can do hypothesis testing and compute p-values, whatever you want to do. K2. Question? Okay, so the only interesting part is now that we interpret it like this is that as X star varies, this you can see the length of the confidence interval is gamma times that standard error, and then the standard error depends on X star. So as I vary X star, this is like gonna adaptively change. And so the uncertainty or uncertainty changes. Um, and the easiest way to see is I'm doing it in the simple linear regression. You can see here the red line is the estimated regression line mu hat. So this is, in this case, it would just be, let's say x star would be just one, let's say x, then mu star. A mu of x would be just beta zero. This is the true regression line. And then mu hat of x would be x star transpose um, beta hat, which just would be beta hat 0 plus beta hat 1 x. So this is just really this line, right? And so that's the red line. And then at each point, if I go at each point, this is going to be, I'm going to just do x here because x star here the vector would just be completely specified by the second coordinate. So if I go at x, this would be mu of x. Sorry, this mu hat x I'm plotting, and this the upper bound would be that mu hat x, the upper bound of the upper end of the confidence interval. So gamma times the standard error of mu hat x. I should say x star to be honest, if you want to be precise. Yeah, so let's not do that. I mean, okay, so rather than writing it mu hat of x star, I'm going to just write it as mu hat of x because it's really a function of x. Okay, just with some abusive notation, it's just rather than being a function of two coordinates, we can also just view it as a function of one coordinate, as one coordinate is fixed. So let's do that, then I get mu hat of x. And here it's going to be the bottom part would be just mu hat of x minus gamma standard error of mu hat of x, where um, the standard error is this, okay? And it depends on x star. Okay, so because that the standard error depends on the location, and we'll see this singular regression, you can easily calculate it. The band, the width of the confidence interval, the band would change. And as you change x, you can just plot these upper and lower. So you get an upper part, which is the upper end of the confidence interval, and a lower part, which is the lower end, and you get the middle. The center would follow a line, but the upper and lower bounds do not follow a line because this would be like a quadratic. Well, you'll see next time. And so you can see that the bands are kind of widen as you move away from the center of the data in the x direction. This is the nice feature of the kind of confidence intervals that we drive. So near the center of the data in the x coordinate, you have more observations, your uncertainty is lower. Okay. As you move away, you're more uncertain because you haven't seen the data there. And this naturally kind of captures that uncertainty. Okay, so in other words, extrapolation is genuinely uncertain. And so you have to be careful. When you fit the data, that's why just the point estimate is not good enough. So being here is less certain than like being here. And so the confidence interval tells you that your estimates are kind of less reliable out there than in the middle. Okay. This is why like traditional statisticians like really like the confidence intervals and like inference. Just giving a point estimate that does not reveal this feature. But once you have the confidence interval, you have extra information where you can be more trusting of your results for your count. Is the nature of these bands clear? So how you get these bands? And you can actually, in the SLR, you can actually calculate it. You just, as an exercise, it's on the next slide, but I leave it as an exercise for you. So you just, X would be like an n by 2 matrix. You multiply things out, you get a 2 by 2 matrix, you invert it, and then X star would be like 2 by 1. And you multiply things out and simplify, you get this result, which is here X bar is the average over the training of X's, and SSX is just the sum of squares of the deviations of Xi from the center. Okay, so this SSX is measuring uh, kind of overall, uh, like if you divide by 1/n roughly, or 1/n-1 roughly, variance, like spread. And so that is saying in terms of the total kind of variance, that the particular point that you're looking at, okay, to be honest, this should have been like x star. Okay, so this is just a single x. Yeah, there's notations around it, but that single x, like the difference from x bar squared divided by SSX. So if x star is exactly equal to x bar, that second term is 0. So you get the narrowest band. This is going to be 1/n. As you go further away from x bar, this is the plot. Um, so 1/n is this constant line here. And then the other term, this as if you plot it as a function of x star, it would be that dashed line. And then if you add them up, you get that red curve. You can say it's minimum at x bar. And as you move away, it starts to grow quadratically. It's a quadratic function. So that's the quadratic feature of these bands that you see. Right. And at the center, you could verify easily because mu hat x bar would be equal to y bar in the simple linear regression. If you go write down the formula at the center, your estimate of regression line would be the average of y's. And we know that the y's are kind of IID. So the variance of this would be 1/n variance of a single observation, which is sigma squared. So this you'd get that it's like 1/n. I'm here plotting just the variance divided by sigma squared, basically. This is the variance of the regression line divided by sigma squared. So variance of mu hat x star divided by sigma squared. If you remember what the variance was, it's just exactly this. So the variance of mu hat at the middle would be just the variance of y bar, which is the average of a bunch of IID variables with variance sigma squared. So we get that. But then as you go away, you get this extra term, which tells you you should be more uncertain, or like your estimate is more uncertain because your observations are sparser out there rather than at the center. Again, you get all of this for free by just a little calculation of the variance. You don't have to guess anything. It's just the formula just pops out. Okay, that's the kind of this parabolic shape that you see here. Okay, it's like if you look at the compared to the regression. So if you imagine like if you rotate it so that that's flat, like horizontal, then you just see that if the red line is horizontal, you see that parabolic shape. Here is more exaggerated, but that's kind of the okay. Yes.
Sorry, it's a simple question, but I'm not understanding why the variance of mu star x, sorry, mu hat x star is taking that form of variance over sigma squared.
Oh, this we calculated already. So this is this result. This is just the variance. This is what we did here. So you helped me write it down. So that's the variance of A transpose we had. So that's really like x star, and then if we divide by sigma squared. Okay. So that's really this result, which is really a renaming of that result if I divide by sigma squared, I guess.
So that's why you're dividing by sigma. Maybe I should just read.
No, just dividing by sigma. I mean, you can just keep the sigma squared because that's the part that is only dependent on x. I mean, this whole thing would, if you multiply by sigma squared, everything would be shifted by sigma squared. It kind of, it doesn't have any particular meaning. It would appear here. So in these bands, it would be, you're going to be multiplying by s actually. So because you would get s squared times this. I'm just isolating the part that's related to x, it's variable with x. It should have been easier to just maybe write sigma squared. If you don't like this, just do this. Maybe more clear. So let me delete Okay. So this would be sigma squared times this. So this would be sigma squared. So at the minimum would be sigma squared over n, and as we go away. And on the bands, this sigma squared is replaced by a squared. Actually, a square root of everything. So it would be like uh yeah, you can figure it out. It's just take the square, replace with s squared, and take the square root, get s square root of this. That would be basically how far uh, and times gamma, how far above and below you go. And this varies. Any other questions? So we get this adaptive, nicely adaptive confidence band for the regression line, kind of without much difficulty, unless that non-nullity assumption. And this is like the calculation which you can do for yourself. There might be some um, typos. I'll just check, please. No questions about this picture or this picture. You pause a little bit. Yes.
Just a quick question. So that doesn't hold in general for like linear regression, right? Only simple linear.
No, in general holds, but it's harder to visualize.
Okay.
Because in this function would be like a quadratic. You can see x transpose, x star transpose. So whenever you have this like x star transpose, some matrix m x star, this is as a function of x star, this is a quadratic function. And then you get the square root, but it's harder to visualize in more dimensions. So you get like a hyperplane, that would be the regression function, and then you get something which is barrel shaped above and below.
Yeah, I was just because the slide said like, in SLR, so I thought like a great thing is SLR.
You mean here or
Yeah.
No, this is just an example.
That's,
Right. This holds in general because of the form of this function. It's just easy to visualize in one dimension space rather than. You can ask ChatGPT or Cloud to just do it in 2 dimensions. In 2 dimensions, you can also visualize, but with 3D, it's easier to just manipulate it by rotating around and seeing the
I'm actually asking for ChatGPT right now.
proof of this.
The algebraic.
Oh, this one? Good. Okay. It would be good to try yourself and then check. I did ask myself as well, so wrote it down. I think there's a typo there. There's like an M, but
Yeah, that's what it showed.
just do it for yourself. It would be helpful. Then try the ChatGPT. Okay. Any other questions? Okay, so this so far has been very like I think standard given the previous lecture. So everything that we did today is like basically repeating with a bit of interpretation, but A transpose B or mu, basically mu of X star, that's not much of a difference. This little piece here is slightly like a little bit of novelty, and that's like extending these ideas to predicting a new observation. That's maybe moderately new. The difference here is that I want to, let's say a new user comes in, or a new, let's say patient, let's say we have it, this is a data set of patients, a new patient comes in, I have trained the model on existing patients, and we're trying to predict some, like, I don't know, blood pressure or like glucose level or something like that, that's Y, and the X are characteristics, age, I don't know, other features of the like various test results and stuff. And so we have like an estimate of all the parameters of the model. We assume a linear model. We have the data hat, and so we have the regression function mu hat. A new patient comes in, like it has a new X, like a new set of covariates and a new response, but the new response we don't see. we just see the covariance, and I want to predict the actual response, okay? And this is slightly different. So the new response would be the regression function applied to the xu plus this noise. So the issue with this is extra noise. So if I want to predict the actual observed response of the new patient, I need to account for this extra noise. And so my confidence intervals will be wider to capture this extra noise. And so this new epsilon nu would be under our E2 assumption normal, which means 0 and variance sigma squared, and it would be independent from all the previous observations. So in particular, it would be independent of y, or if you could want to say, it would be independent of the training noise, which is just like epsilon y up to epsilon n, the ones that we saw in the, let's say, training or during the fitting. Okay. So you're going to use that fact. Okay, so the key is, if I want to predict y nu, if I want to give a point estimate, it's still the mu of x nu is the, or like an estimate of x mu of x nu is the best prediction, point prediction, because the mean of epsilon mu is 0. If I want to give it like a one estimate, we can use the mu hat x nu again. But if I want to give a prediction interval, the variance would change. So these two distinct ones. If I wanted to estimate just x nu, just the mean response of the new patient, I could have just used mu hat x nu. If I want to actually predict, let's say y nu, we're going to still predict it by mu hat x nu, but if I want to build a prediction interval, that would have to account for the extra noise. Okay, so y nu is the actual nu value, which is predicted by mu hat. The other one is estimated by mu hat. I mean, I'm not going to worry too much about it. The wording doesn't matter. What matters is you understand the extra variance. So in order to see, let's say try to build a confidence interval for y mu. The idea is to do this decomposition. So mu hat x nu minus y nu. If I plug in this equality here, so I just plug in what y nu is, I get that decomposition. So I get mu hat x nu minus mu x nu. This is my estimation error. It's the error in estimating the regression function at this new data point, and then minus the mu noise. Okay. And so this is really x nu transpose times beta hat. And if you recall, beta hat is the function of y. It was, so this is really a the whole thing is an affine function of y and epsilon mu, so it would be Gaussian, because y and epsilon mu are jointly Gaussian. And in fact, this whole thing, because of unbiasedness of mu hat, for mu, this ends up being just a function. You can show that this is a linear function of really the epsilon, the noise. This you do in the homework problem. And so this whole thing would be like a linear function, let's say whatever, m times epsilon and epsilon mu. You can write it in that fashion. Okay, so it would be actually a vector because it's scalar. So let's say there is some m that you try to figure out that would be like m transpose times this vector, and this pair, this is like an n plus 1 by 1. So the top is n by 1. You know, like the bottom is 1 by 1. So it's n plus 1 by 1 vector. Because epsilon and epsilon mu are independent, this whole thing would be jointly Gaussian. So it's like a linear transformation of this, so it would be Gaussian. And the mean would be 0 because, as I mentioned, the first half is, because of the unbiasedness that we showed, this estimation error is 0 mean, and the epsilon mu is 0 mean. So this quantity would be a Gaussian, it's 0 mean, it's a scalar. The only thing that you have to figure out is the variance. And then you can argue that because this part only depends on epsilon, and this part only depends on epsilon mu, and they're independent, so the variance decomposes. You get the sum of the variances. Okay, so the variance of this piece we already calculated. That's going to be just Yeah, so you should get two sources of variability, the variance is that. So what you get is the variance of that piece would be, the first piece would be this part, which we already calculated. The variance of the second piece would be sigma squared. Okay, so you get, so variance of this would be sigma squared x star transpose, or sorry, x nu. X transpose x inverse x nu. And the variance of this part, I mean, negative sign doesn't matter. So the variance of this is sigma squared. So the variances add up. So that plus that would give me, you factor out one sigma squared. So you get that result up there. Okay, the details I'll let you figure out in your homework problem. It's just the only thing that matters here is just that you have this extra noise. So you get this extra feature in the variance. And then the standard error, let's say for prediction, would be just the square root of this and sigma replaced with s. So you get this piece here. Okay. Does that make sense? So then, I mean, this is again the same setup. So you have this new quantity. You can build a pivot. You can subtract the mean. There's no mean, so there's nothing to subtract. And then divide by the standard error. Again, by the same argument, this would be t and minus t minus 1. Okay, now this is kind of a pivot in a sense, although we're not having a parameter here to try to estimate. We're just trying to build a confidence interval for y mu, but exactly this I mean, is placed exactly where we used to place the unknown parameter. So you do the exact same arguments, you end up with this confidence interval. So the center would be here times gamma, the plus minus gamma times this standard error. That would be the prediction interval. So if you compare it with the confidence interval for the regression function, the center is the same. The fact that gamma is the same, the only difference is that the standard error. The standard error now has this extra plus 1 under the square root, which y doesn't. And that's exactly the amount of noise, the added noise that we're trying to capture. Okay. So even at the center of the data, as the sample size goes to infinity, so that the first like term would go to 0. The estimation error, this part, in general, when you have more samples, the estimation error is going to go down. It's kind of not obvious here, but it's obvious in the SLR, or in general, this term. So you can see this variance. If you really want to be maybe theoretical, if you want to understand theoretically, what you do is you divide by n and multiply. So I can write this variance as sigma squared over n, and then I have to multiply by n. But I'm going to move the n inside the inverse, and so it would appear like x nu transpose x transpose x over n inverse x nu. Okay, so this I can rewrite like that. So that's the variance of that estimation error part. So this is really variance of mu hat x nu minus mu of x nu. I mean, it's also the variance of mu hat because centering doesn't change the variance. But in this stabilizes. If you have done one of your homework problems, this is like an estimate of the covariance matrix of X. As n is grows, this is going to approach the second moment actually. If the X's were random, this would stabilize, so this would stabilize, and so this is how things would go down, sigma squared over n, which was seen before in the SLR. So in the general case, this error is going to go down like sigma squared over n, and so you get a more accurate estimate of mu hat. And so if you look at just the confidence interval for the mu hat, it shrinks to 0. But in this case, because of that extra 1 remains. So it's not going to shrink to 0 because you have a new observation coming in, a new piece of noise that you can't like remove. That's kind of the fundamental noise level of the problem. Okay, so this is in the limit of n going to infinity. This is not going to shrink to zero. In other words, you can also, another way of writing it is that you have a standard error of prediction squared is the standard error of mu hat squared plus squared. As you get infinite data, this first half is going to go to zero. The second piece doesn't go to zero. Okay. And you can also see it's always wider because this is going to be always bigger than this. So it's a square root that's going to be always bigger because the squared is always non-negative. Okay, so prediction interval is always wider. And even if you have infinite samples, it's going to not shrink to zero. You need at least one standard deviation of noise to capture the new noise. And yeah, as you go to infinity, the t also approaches the Gaussian. So really, the gamma also approaches that of a standard normal. So you really end up like just having a confidence interval to capture one standard normal random value. But that piece doesn't matter that much. Okay, here's a plot. So on the same plot, we're also doing the 95% prediction interval for y mu. Okay, and you can see it's wider. Okay, and the interpretation is that if I have a single x star and I draw many samples from this model with that x star, then 95% of the new observations are going to be in that band. It doesn't tell you that 95% of all the observations across all the x's are because we're fixing a single x. So that's not going to be, I mean, we're lucky, like we have few things here. Everything's kind of light in that band, but that's not what this means. So any questions about this? This so far is just the only new idea here is that if you try to predict a new observation, you have this extra noise, and then so you have to account for that, and that would explain the variance by just sigma squared, and so you get a wider band. Nothing else is really new. The rest of the construction. So, questions? Okay, so one slide that I'm not gonna go too much about. All of this was kind of pointwise, the so-called pointwise coverage. So what we have, let's go back to the confidence interval for the regression function. What we showed really is that the probability, so we have a confidence interval at point x star such that mu x star belongs to it with probability 1 minus 1 half, sorry, 1 minus alpha, and separately for each x star. So if I fix x star, this is in a hold. It doesn't tell me, this is called pointwise coverage. It doesn't tell me this. If I wanted to have an interval such that the probability that mu x star belongs to the confidence interval for x star for all x, so that the all x is inside the probability. Okay, this is a much stronger statement, and so that first version doesn't, I mean, it might not be obvious, but that first version, if I fix one, then this holds. But if I want a statement that simultaneously holds for all x star or like a sequence of x star, then I need this stronger version, which we don't have. So if you want something like that, there are multiple ways of doing it. There's a classical approach, the so-called working hot link. It's like a very long time ago, that you can change that like multiplier of the confidence band by something which is related to the F distribution. This one you can actually figure out later in the course if you want. But at this point, I'm just going to point out that there's this there, and there's another one which is like more common. It's like the Benferroni correction. How many people have seen this? Yeah, okay. So good. So this is like you just replace the alpha by a small number. So if you want, like maybe you want to guarantee it, like the confidence interval simultaneously holding at like 5 points, then you divide your alpha by 5, and by the union bound, you can be like guaranteeing that. Maybe I'll talk about this next lecture. We want to do general linear hypothesis. But that's another simple approach. But this is kind of generally like the multiple testing problem. And we have a very nice solution for a variant of this, like not exactly this problem, but we want to have basically like test multiple hypotheses about data simultaneously, and they're all linear. We don't have to do this correction because that would be like a loose map. We could do much better. But just have these in mind, I mean, in case you want it. What I want to talk about, which is the interesting part, the more modern approach, which we have maybe like 7 or 8 minutes to talk about. And if I run out of time, let me come back and talk to go later, maybe next week. Is what happens um, if these assumptions are not true. So we made a lot of assumptions. So we have like y is x beta plus epsilon. We're assuming that actually the linear model holds. The observations follow this, and we have e true. So our prediction interval, let's say, the one that we just constructed for a, y, mu, relies on the Gaussian errors and the correctly specified linear model, okay, which are very strong assumptions, to be honest. Okay? If they're violated, you're not going to be like, you're not going to get these guarantees. Maybe if they're slightly violated, you're still close, but you never know what the real model is. So the way that it could fail is that you could have nonlinear truth or heavy tails or contamination or heteroscedasticity, which is like unequal variances on the noise. We assume equal variances. There is a way to handle that later in the course if we know exactly how they vary by a generalized least squares. But if I don't know, let's say if I assumed it, but they're not actually equal variance, these would go away. Yes.
Combinations.
Contamination, let's say you have like maybe like a fraction of the data points are from some other model. So let's say you have a linear model, but the fraction is just like maybe someone actually mistakenly recorded. This really happens in like experiments. It could be like completely junk. Okay, that's possible. I mean, you could just maybe like it doesn't really happens in practice. Some people do experiments and the device is not attached, maybe, and just record noise basically instead of just recording. And like half the data is correct, the rest like someone just switched off the device and just recorded noise, and you don't know. Okay, and that would change it. This happened to me like in postdoc. Like, we worked on a problem and decided at the end that the data was junk. So there was no signal in it. It's very like possible. Anyways, so can we get a TI that works without these assumptions? Okay, that's the modern take, and there's a very interesting idea that let's make minimal assumptions. What can I do? If you make minimal assumptions, your conclusions wouldn't be as strong. But surprisingly, there's a very interesting way of doing this. The answer, like the common thing that people are now very much using, is this thing called conformal prediction. How many people have heard about conformal? Okay, good. I mean, you'll learn something new in this course then. And then those are the people involved early on, and then we find later by Jingwei, Larry Wasserman at the CMU, and many others nowadays. Emmanuel Candace at Stanford, and their students and so on. So it has been a very hot topic in stat. So it's distribution free, this approach, and it's valid for finite samples. It's not asymptotic. Around any predictors, that's the interesting part. So you don't have to have a linear model. You could have a tree-based algorithm. You could do XGBoost or like any ML model, like neural networks or deep learning, anything, like any prediction model that you have, it just works for that. And it's very now commonly used in production ML, like machine learning in practice for uncertainty quantification, because it's really minimal thing. So the same assumption that I made is that the data are exchangeable. So weaker than IID. Currently you're assuming, so my data is, I have these pairs, xi, yi's, right? I from 1 to n. We assume that the xi's are deterministic, yi's are random. In this framework, we're going to assume that both xi's or yi's are random. Okay, for each individual, I get a vector, basically. Imagine. Let's say I have 3 data points. I get x1, y1, and I can also stack x2, y2. And also attach x3, y3. I mean, usually we look at it as a set. I can also like stack them in a vector. What we assumed before is that these are independent. I mean, if you go to the random design, if it is a random design, the standard assumptions that we worked with would be just to assume that these are IID. Okay, the x's are drawn from some distribution, given the x, y is drawn as like, so xi is drawn from some distribution, and then given xi, yi is drawn from the linear model. So it would be normal would mean beta transpose xi and sigma squared. And these are independent. So independent. And then across I. So these are independent across I. So that's the random design version of the model. And you can see conditional, we have been basically working conditional on x's. And so the only assumption that this new framework requires is the exchangeability. What it assumes is that if I stack these, basically if I reorder, so if the distribution of this whole vector will be the same if I switch some of the guys, the orders around. Like the second sample, I look at it first rather than like I switch the order of the first and second. Okay, so this whole vector, there could be dependence. The reason why I put it on a vector is that there could be dependence among them. So you have a giant joint distribution among all your samples. The only thing that I can say is that if I switch the order of things, in any order, the distribution doesn't change. And this is really minimal because let's say in practice, what it means is that the conclusion that we want to make, it doesn't matter if we, like let's say the first patient comes in first, like you come in first and your friend comes in next to the lab versus vice versa. So that doesn't change the relation between XLs. But your responses and your X's could be highly correlated. So if your cousins, so two cousins could be very much related to each other, but whether the first cousin comes in first or the second doesn't matter. So this is a minimal assumption. And just bear with me just one more slide. So under this, there's this very simple approach. It's called a split conformal prediction. There are many variations, but this is what you could do is you can split your data into 2 pieces. One piece, let's say NR sample and training sample will be N training, and then the calibration set. And what you do is that you feed your predictor, let's say your linear model on the training set, and then you calculate the residual on the calibration set. So yi's, those new hat xi's are in the calibration set. You look at also the residuals, and then you look at the empirical cubed hat quantile, which is this at this level, and the empirical quantile of these, let's say, scores or absolute values of the residuals. And for a new data point, this would be your center, and you just add plus minus this quantile. Okay, and then you can guarantee that that if the calibration data and the new data are exchangeable, then the probability that y new belongs to this interval is going to be bigger than or equal to 1 minus alpha. Okay, that's with minimal assumption, you get this kind of an interesting coverage. And next time I'm gonna come just look at these slides and then try to understand. It's a very simple procedure. You just train on one part of your data, and then you calculate the residuals on the calibration set that you haven't used in training. And then basically you look at the absolute value order, then you pick the quantiles are basically, you look at like, for example, the K guy is decided by that factor, which is dependent on the sizes of the relative sizes of the calibration site and size on the alpha. And then you just widen like your width of the interval there. And this is guaranteed to cover at the level of okay, so we're out of time. I'll The slides are on there, so just have a look and next time I'll come back and talk about this.